Lab 2 of Physics 2012 for the spring semester of 2021. To begin the lab, I first obtain a video of me dropping a can, upload this video into Tracker, and create a graph that observes the motion of the falling object. I then used this observed data to create two computational models comparing the motion of the falling object, one taking into account only the force of gravity and the other taking into account the force of gravity and drag forces. Through these two models, I'm able to draw conclusions on drag force, gravity, and the motion of the object. Using Tracker, I modified my axes and updated the properties of my can so that I could obtain an accurate description of data. I did so by entering the known mass of the can and calibrating my known height into Tracker. I modified the axes so that the initial position of the can was at the origin, and I observed that the final position of the can was at negative 1.715 meters in the negative y direction. And this final position was observed after a time of 0.601 seconds had passed. Here's the model of my can observed falling in the negative y direction versus time. As we can see, the object is not moving at constant velocity because the slope is not linear. This indicates that there are forces acting on the object, causing the net force to not equal zero. We can observe through the equations of Newton's second law that the non-constant net force indicates a non-constant velocity. Therefore, according to Newton's second law, we can see that the non-constant velocity would explain how the position versus time graph is nonlinear of our observed can. To model the motion of the falling object, I first created a model that took into account gravity forces acting on the can. As you can see in my code, I updated the mass of the can and known initial conditions that I obtained in my data through Tracker. I set the gravitational force to equal 9.8 meters per second because this is standard for on Earth. And since this model does not take into account drag force, I set B to equal 0. I then updated the forces acting on the ball to only be gravitational force, which is the vector 0, negative mg, and 0. And I coded my data so that the model would only run as t is less than 0.601 seconds, as that's how long it took for my can to fall in real life. I then graphed my observed data and predicted data onto the same graph to observe the accuracy of my predicted model. As we can see, the gravity model overpredicts the downward velocity of my actual model, and this can be explained by the absence of a drag force coefficient in the coding for the computational model of number 1. Therefore, in the second model, I graphed the motion of the objects while taking into account both gravity and drag force. All my conditions remain the same except for the net force acting on the object as it falls. Drag force can be modeled as force equals the negative drag coefficient times velocity squared times the direction of motion. Through guess and check on my coding, I found my drag coefficient to equal 0.002, and I set the forces acting on the ball to equal gravity and my drag force. After graphing my observed model, gravity model, and gravity drag model onto the same graph, we are able to observe the accuracy of all three graphs. As we can see, the drag model is a better prediction of motion of the falling object, though it's still not perfect. This could be a result of many factors, such as a tilted camera angle when I recorded the observed video, or the movement of the object on a horizontal plane, not just the vertical plane, as we are predicting here. The model that accurately obtains terminal velocity between gravity and the gravity drag model is the drag force model. As the Lab 2 instructions describe, terminal velocity happens when the force of drag pointing up has exactly balanced to the force of gravity pointing down. In other words, this means that when an object has reached terminal velocity, the net forces acting on the object equals 0. And according to Newton's second law, when the net force of an object equals 0, this indicates that the object is moving at constant velocity. This would be reflected on a graph with the most linear position versus time data. As we can see, the model with drag has a slightly more linear graph as time moves on because the drag model shows the object reaching terminal velocity. While it's slight, you can see how the graph is flattening out a little bit at the end, whereas on the model without drag, the graph does not seem to have a slope that will eventually flatten out. This can be observed a little bit better on the graph of all three models, where we can see the observed model and the drag model ends flattening out a tiny bit together at the end, whereas the graph of just gravity shows no sign of the slope flattening out, and it still has a complete curvature of slope. And while on the topic of terminal velocity, we can observe whether or not an object will always reach terminal velocity with drag force. By comparing an object drops from rest, or the object we observed from this experience, with an object that was thrown downward, we can observe that despite the difference in initial velocities on the graphs, eventually the slope evens out. This flattening of the slope indicates a net force of 0, and thus the object reaching terminal velocity. As we can see in both cases, terminal velocity is reached eventually. The only difference is the matter of time it takes for the objects to reach terminal velocity.